Now in this session we'll be discussing another violation of the classical model, which is autocorrelation. The recommended readings for this unit, but this particular topic are chapter 10 of Gujarati and chapter 12 of Gujarati. Chapter 10 of Gujarati, just leaving aside these sections 10.6 and appendix 10a, everything else needs to be covered. For Gujarati, only these are the preferred, recommended pages. Okay. So before we can discuss what basically the problem of autocorrelation is, just a brief review of the difference between disturbance and residuals. So if you recall in the beginning when we started the OLS model, and if you have read Gujarati by now, you would have come to know that uh, there is a population regression function, there is a sample regression function, and Gujarati likes to the disturbance term, the term UI in that population regression function. Let me write that as well. Yi equal to beta 1 plus beta 2 xi plus u. So this is basically the, you can say, the error the error term, and Gujarati calls it error. He also calls it the disturbance term. Okay. When we estimate these two parameters, we get what is known as a sample regression function, and the error term, okay, the estimated error term in this model is basically called the residual, and it is represented by this term EI. Okay. So in fact we'll be using these notations, so it's very important to have them clear right in the beginning. Okay. So the OLS model assumes that there is no autocorrelation. More formally, it means that expectation of ui times uj is equal to 0 for all I not equal to j. Okay. Just a small clarification here, which is what will happen if I say I is equal to j. So if I say I is equal to j, this becomes expectation of ui times ui, or expectation of ui square, which is basically the variance of the error term. Okay, sigma square constant. So that's why we have the not equal to sign here. We're basically talking about the disturbance terms coming, as in the disturbance term from, you can say, so if I draw a data set here, if I just write a data set over here, y and xi, and let me call this the ui, the true error term. So if I just fit in the model, and let me call that model y hat. Okay. So this is the true value of y, predicted value of y. So a difference between these two values for each observation, the difference between these two is what constitutes my disturbance term. Okay. So what they say is that disturbance term, let's call this u1, let's call this u2, u3. So disturbance term, um, for the first observation, second, third, they are not correlated among themselves. That's the basic idea behind this assumption of no autocorrelation. So as I said before, that one of the obvious assumptions is that there is no autocorrelation among the disturbance term entering the PRF. So as I said before, uh, in the previous slide, that this UI basically represent the disturbance term in the population regression function. Okay. But we never observe the PRF, we rather estimate the parameters of PRF. So what we observe is not the true disturbance, which is UI, but their proxies represented by EI, okay, also called residuals. So now this is like one definition of autocorrelation, which was given by Candle and Buckland 1971. It says that autocorrelation is a correlation between members of observation ordered in time, as in time series data, or space, as in cross-sectional data. So remember, cross-sectional data is basically a data that is recorded, or the data that is observed at a given point in time, is observed at a given point in time. All right. Time series data would be something like the GDP data. So you have, let's say, if I'm looking at a time series data for India, okay. So I'm looking at the GDP numbers from say 1999 to 2016. So if I arrange this data, it's coming in an orderly fashion, and I'll call this data as time series data. Okay. So it's very common to find autocorrelation among the observations in time series data. It's in fact very common. Even it's common in the cross sectional data if there is like huge heterogeneity of among the units which are being sampled. Okay. Thus, autocorrelation can occur in time series data. However, it can also occur in the cross-sectional data, in which case we call it spatial correlation. So, with respect to time series data, we use the term autocorrelation. Auto means within the same, like is basically a term that's used auto. I mean, generally it means that with respect to time only. So, whereas if it occurs in the cross-sectional data, we call it spatial correlation. So now we are looking at different patterns of autocorrelation, and you can see that there are different patterns which are being shown here. So you can see this one is like sort of upward sloping, downward sloping pattern, parabola. It's almost like a cubic function over here, and on y-axis we have the uh, error or the residual term. I mean, they show U and E both, but naturally you never observe the U, you only observe the E. And on x-axis we have the time. Okay, now the only desirable pattern, okay, the only desirable pattern is basically the one given in E. Let me erase this, and in case it's covering the entire chart. Yeah, so this is the only desirable pattern. That is basically there shouldn't be any pattern. There shouldn't be any pattern. Okay, so if I if I see any like if I plot all the residual terms against time, I should not observe any kind of a pattern, and this is the only graph which satisfies the OLS assumption of no autocorrelation.